We're still going to practice some more calorimetry problems here on Energy Practice 1. So the next question is asking for how much energy is required to condense 670 grams of water. So right away, question you're asking, is this a phase change or a temperature change? So a little bit of a clue here, there's no temperatures included in the problem. So that's indicating that this is a phase change. For our problems, phase changes are going to use Q is equal to delta H, N delta H. There should be an N there. The reason we're using N delta H is because of in the values that were provided to us, we were given them in kilojoules per mole. So since they're per mole, we have to make sure our units are canceling. So we are condensing. So when you have a phase change, I always like to think of what is happening. So for condensing, we're going from a gas to a liquid. In order for this to happen, we need to remove energy, and when we remove energy, we're going to have a negative number. So we have to convert, first of all, the 670 grams of water into moles. So this is a simple mole conversion. 1 mole of water is 18.02 regardless of what phase it's in. So that will allow us to have moles of water. So you should get 37.18 moles of water. So that's our N value. We now just need to figure out the delta H. Okay. So for the values that are provided to us, delta H of fusion is for melting when you're going from a solid to a liquid. Well, that doesn't help us. Delta H of vaporization is going from a liquid to a gas. So vaporization is the opposite of condensation, which is what we're doing. So we're going to use this value. The only difference is we're going to put a negative sign in front. So we're going to put 37.18 mole times negative 40.7 kilojoules per mole. Condensation and vaporization are opposite processes. One, we're adding energy to it. One, we're removing, so we're able to calculate it that way. So I always think of what I'm doing in order and what sign I should have in the problem. That helps me to make sure that I'm calculating it properly. So you end up with negative 1,513.26 kilojoules. Which is a lot of energy that needs to be removed. You should round this to sig figs, either 3 or 4. I would probably do 1513 kilojoules here, but 1510 would also work as the correct answer. Okay, so up to we've had only one process occurring. So we've either had one phase or one phase change. The thing of it is, sometimes we have more than one thing happen, though, and we have to kind of break it up into the components. So for the next one, we're asking how much energy is required to change water from 112 to 85 degrees Celsius. So with 112, we have a gas, and 85, we would have a liquid. So water boils at 100 degrees. So that's where our phase change is going to occur. So if you think of our graph that we had, it went like this. Every time you go to a different angle of the graph, you have to do a different calculation. So for us, 85 is about right here, 112 is about right here. So we have 3 different areas of the graph, meaning we're going to have to do 3 different calculations. So I like to write this out before we go any further. So we need to go from 112 degrees Celsius to 100. This is all going to be as a gas. I can't go any lower than 100 and still have a gas. That's how I know to stop at 100, because that's where the phase change occurs. Then I'm going to go from a 100 degrees Celsius gas to a liquid. Once I have a liquid, I can go 100 degrees Celsius to 85 degrees Celsius. Both of those would be a liquid. So potentially you could have a 5-step problem here. Would I give you a 5-step problem? Probably not, but you could have a 5-step problem. Sorry, I just noticed in the answer above it should be negative 1513 or negative 1510. You want to make sure you don't forget your negative sign in your final answer like I just did. It is a common error. For the phase change here, you could put 100 degrees Celsius here for both of them, because when we have a phase change, we don't change the temperature. We only can change the temperature after we have one consistent phase. So it is a 3-part problem. The interesting thing about this problem is that it doesn't give you a mass, which is a problem. So we're just going to say we have 75.0 grams of water. So I'm going to start with the first part here, going from 112 to 100 degrees Celsius. So we're cooling the gas for this to occur. So let's start with blue. So because we're changing the temperature, we're going to use Q is equal to mCp delta T. So we have our mass is 75 grams. We can get our specific heat. Right now we have a gaseous water. So we look at up in our table, and then for the specific heat capacity of a gas, we have the value right there, 1.996 joules per gram degrees Celsius. And then we're going to have our temperature. So we're going to take our final, which is 100, minus initial. Okay, so when we do that, that's going to be a negative 12 difference for us. So we can now calculate the Q, or the heat, here. So we get negative 1,796.4 joules. We're going to probably round this to 2 or 3 sig figs. For these multi-step ones, I would just honestly at this point keep them, I would keep 3 or 4 sig figs, because we're going to have to kind of add it up. So for this right here, I'm going to just write the amount, because that's going to be our last step to add them all together. So right now we have 1,796 joules. So then we can do the next step. So for the next step, we have a phase change, which we use Q is equal to N delta H. So we're going to be using the same delta H as the last problem, because we're condensing water. So our delta H is negative 40.7 kilojoules per mole. We just need to figure out what is 75 grams into moles. So we have to do a quick mole conversion. 75.0 grams of water. 1 mole is 18.02 grams. Okay, so we end up with 4.16 moles. Now the nice thing is if we had a second phase change, we already have the moles. We could use the same number again, but we don't only have one phase change in this problem. So we're going to multiply these together. We should end up with a negative number here. So we end up with negative 169 kilojoules. So while we still have one more part, something to point out, notice we have joules and kilojoules here. This is going to be a problem for us. We're going to have to fix it. We have to make our units match. But for right now, let's just finish the last conversion. So we're going to go 100 degrees Celsius to 85. It's going to be very similar to the first one. It's, again, Q is equal to mCp delta T. We have our M is 75.0 grams. We'll get our specific heat from the table above, which it's the water's liquid specific heat capacity is 4.816 joules per gram degree Celsius times the change in temperature. So we're going to take 85 minus 100. It's always final minus initial, which this would be negative 15. So we can now calculate Q for this. So just want to point out here, in the value in my problem, it should be 4.186. I had flipped the 8 and the 1. So make sure you make that correction. You should end up with negative 4,709 joules, which we'll write right over here. Okay, so we have joules and kilojoules. They're all negative values. If you're doing these problems properly, they should all be the same sign. It's not. If they're not, that means you're cooling, then heating, then cooling, which isn't something that we would do in a problem because it won't help us. So we need to fix our units. We need to make them match. So what I would probably do is take kilojoules and make it into joules. There's 1,000 joules in a kilojoule. So it would be negative 169,000 joules. And this helps to kind of illustrate the scale here. And negative 1,796. So the majority of our energy here is from the conversion of a gaseous liquid to, or a gaseous substance to a liquid. That's where the majority of our energy is going. I'm not going to be too particular here with sig figs. You would just add these numbers together. So when you add them together, you get negative 17,000 or 175,505 joules. Again, not overly concerned with sig figs here. Just kind of keep whole numbers and kind of do the best you can with sig figs. Don't give me like 2, don't give me 1,000, and we'll be good. So in the next problem, we have a 16.8 gram sample of ice at negative 21 degrees Celsius is heated to water at 68 degrees Celsius. Find a change in heat content in the system. So we're heating, which is the opposite of the last one, but we still have multiple steps here. So we're starting with ice, which is solid at negative 21 degrees Celsius. We can only stay a solid for ice until 0 degrees Celsius. So that's my solids part. Then I have to have my phase change. So I'm going to go 0 degrees solid to 0 degrees liquid. Then 0 degrees Celsius to 68 degrees Celsius as a liquid. So part of these problems is knowing when your phase changes occur and what that means. For us, we're going to be working with water. So we have two main points. We have the 0 degrees Celsius and the 100 degrees Celsius. If it's another substance, it would have to be very explicit in when the phase change occurs, if there is a phase change. Okay, so we have 3 parts. First part is dealing with our ice sample with a temperature change. So we have a temperature change, so we use the Q is equal to mCp delta T. So Q, our mass here is 16.8 grams. Our specific heat capacity for solid water, we take a look at our chart. We find the specific heat capacity of solid water. It's 2.108 joules per gram degrees Celsius. And then our temperature change. So for this one, we're going to have 0 minus negative 21 degrees Celsius. So this would give us 21 as our temperature change. So for the first part, we end up with 743.7, so we're going to just round it to a whole number, 744 joules. So that's just the amount of energy required to bring it up to 0 degrees Celsius. The next part is a phase change. We're going to have Q is equal to N delta H. Okay, so we have to do a quick mole conversion here. We have to take our 16.8 grams. Nice thing is, too, since we're always using water, we have the same molar mass. So 16.8 divided by 18.02 will give us the moles. So we're going to have 0.932 moles. So we have to use the constant for a solid to a liquid, which is the delta H of fusion. So we'll have 6.03 kilojoules per mole. So we'll be left with kilojoules again. So you'll get 5.62 kilojoules here, and then the last step where we're taking our water sample and we're going from 0 degrees Celsius to 68, so it's Q is equal to mCp delta T because there's a temperature change. So our mass is the same, 16.8 grams. Our specific heat is 4.186 joules per gram degree Celsius because that's the specific heat capacity of a liquid. And then delta T is going to be 68 minus 0, which is 68. So we'll end up with 4,782 joules. Then we just have to add them together. I would probably do the same thing I did in the last problem and convert my kilojoules to joules by multiplying it by 1,000. So we'll have 5,620 joules for the phase change. So we're going to just add these values together. I always like to do it with my little chart that I made just to help me make sure that I have consistency. I'm going to add these up. So you end up with 11,146 joules total from this.